In this video, I'll be providing a tutorial for the Multivariate Conditional Simulation component, which is new in Supervisor version 8.14. So to get started, I'm going to add some data to my project. So I've got a small data set prepared already, which is a 2D data set, which will allow us to run the component a lot quicker than if we were to use a full data set. But this is live data, it's an academic data set that's used quite often, and it is going to show us exactly how the process works and all of the benefits of the component itself. So in order to run the component and add the component to our project tree, I do need to organize my data into domain over assay. So I'll do that now. And the four assays which I'll be using for my multivariate data, which I'll be generating the simulations from, are iron, alumina, silica, and manganese. So I'll go ahead and load that now. And as you can see, this is a 2D data set. If I swap over to the 3D viewer, we can see the data here. Show that, iron, just as a percentage of the data. And I guess most importantly, it's the high grades in the top and the low grades in the bottom relative to each other that we'll be looking to reproduce. So adding the multivariate component is as simple as right-clicking on the domain level and selecting the multivariate simulation component. Immediately we're given these views here. So we've got all of the tabs for the component over on the right side. And in the middle is where the Gaussian variance and mean results will be populated once the simulation has been run. So first we need to select all the assays that will be used. The software will automatically see which assays are beneath the component and add them and check them on the right-hand side. So I'm going to be using all four of our components. It is a multivariate data set. We can check the correlations between the variables by adding some scatter plots, and we can see that we have some very strong correlations, particularly between iron alumina and iron silica that we'll be looking to reproduce, as well as some pattern in the correlations between iron and manganese, which will also be reproduced through this process. So first I need to determine whether I use a compositional transformation. So I am using compositional data. I know that I'm in percentiles, and therefore I will need to have a compositional value that totals to 100 or 100%. And because I also know that my data set for each of the sets of four variables will not add up to 100%, I also need to apply what is called the filler variable. And this is just the everything else. So if my iron, alumina, silica, and manganese adds up to 80, then the filler value will be 20 for that record. The type of transformation that I'll be using today is the additive log ratio transformation. However, we also offer the centered log ratio and the isometric log ratio transformations. For more information on those, you can refer to the help file, and there are some references there if you are interested as well. Second, I need to determine my multivariate normal transformation. So I won't go into the details of multivariate normal transformations in this video. If you are interested in those, again, refer to the references in the help documentation. So we have the two options, PPMT and GPCA. Now for the benefit of this video, I'll be using GPCA, and I'll be applying 30 iterations, which I know will be more than enough for the data set that I have. Once I'm ready, I can just hit transform on the property panel there, and Supervisor is automatically going to go ahead and transform the four variables and the filler variable, which is generated, into compositional space. And you can see that the filler variable has become the denominator and been dropped from the results. And then we're going to take these compositional data sets and transform them using GPCA into a multivariate normal space. First, we want to validate the plots, so we check the scatter plots which have been automatically added for us, and we can see that for each of the independent factors we appear to have normal distributions, and we have decorrelated them relative to each other. Each of the ellipses shown in this visual here are the confidence limits expressed by these values here, so 25%, 50% and 75th percentiles, and we can see that from the results we get a relatively good result. Next we need to do the variography for each of the factors. So I'm just going to go ahead and do a quick update on all of these factors, and it's worth noting that for this demonstration I'm not going to spend too much time on the variography itself. So I'm just going to go through and give some fairly general shapes and just adjust where I feel is necessary from the auto fitting that has been completed. And you'll notice that all of the tools that we've got available in these are the same variogram tools that are available for our normal processes. You utilize them in exactly the same way, and we've added them automatically just to assist users in making sure that they have everything that they need to run the process without needing to do any additional manual processing. Once I'm satisfied with my variography, I can go back up to the multivariate simulation component, and I can move on to the next step, which is defining the simulation region itself. So I'll be generating 10 simulations or 10 realizations. I'll be keeping my seed at 999. And for this demonstration, I'll also be just generating my nodes from a specific region. I could, if I wanted, load in a block model and then use that block model as a blueprint for my region. But in this case, I will just set up the region manually using the node definitions. So Supervisor will automatically choose the minimum and maximum coordinates for the dataset, and then I will just specify the block size which I feel is appropriate. I'm just going to use 1 point per block, so effectively this block size is defining my node grid, and I'm not going to worry about putting any restrictions for the node sample distance. If I wish, I can view the extents of my simulation or where I've proposed it in the 3D viewer, and once I'm satisfied, I can move on. The final thing which I need to define is the variography and sample parameters for the simulation. So Supervisor, because it added the components for each of the factors, the variography itself, then it already has mapped together where those are in the tree to each of the independent factors. Keep in mind that if you do change or move any of those continuity models, then you will need to remap the variograms to the factors using this dialog box here. For my search range and search angle, I'm just going to use the variography which I defined, so I'm going to leave those as the defaults. I'm also going to not use assign data to node in this instance. I'm going to leave most of my search defaults as they are, but I will add in some octant restrictions just to prevent some of those extreme edge samples being estimated. Once I'm satisfied, I can go ahead and update this component. So Supervisor is now running each of the simulations which I've defined. I've requested 10 realizations for my multivariate simulation, so Supervisor is just figuring out how many simulations it needs to run of each of the variables so that it can put them back together into 10 unique realizations and back transform them through the processes back into raw space. So the results that Supervisor has given me, it's generated 2 simulation sets, which then we can take the individual independent simulations from, and we can see some results here. Again, looking at the ellipses that we have defined and determining whether we are satisfied that the simulation has performed well. Additionally, we can have a look at the Gaussian and mean variance results for each of the independent factors and see if we are happy with those results. Then finally, we can look at the back transformed results back into compositional space, and then the further back transformed results into raw space. So because I defined a 2x2x2 block, we've reblocked into that configuration. And two main validation components are available to us, one being the model validation plot, which is effectively the same as the model validation plot in if I were to add it to the point data, except it is already referencing the simulations and the point data which generated those simulations. So we can determine which variable we want to compare with the point data and which simulation and variable we wish to compare with the simulation data. And then we can start making some judgments as to whether we feel that the simulation performed as we expected. So in this case, we can see that we have fairly good reproduction of the point data in our simulation, and then we could start to make some further insights on that. If I check one of the other variables and run this, we can also see similar comparisons between some of our other variables. So in this case with silica, we could then make a judgment as to whether we were happy with the result, and in this case we can see that there is a fairly good reproduction of both the input data as well as spatially across the data set. One of the other valuable tools that we can use is of course the 3D viewer, and this allows us to visualize the grades in spatial sense across the deposit and compare them back to what we saw previously in the point data. So in this case we can see, again colored up by FE in percentiles, that we are getting for simulation 1 most of the high grades relatively distributed in the upper regions of the deposit, and a lot of the low grades distributed along the bottom regions. So this is following the characteristics that we saw in the point data previously, and we can see that there is also some interspersed high and low grade values as a result of the simulation as well. So we can look at this across the various simulations if we wanted to. If we had a 3D data set, we could have a look at them orthographically. We can get a perspective view if that assists in our interpretation as well. And we can just validate that we are seeing the characteristics of our input data coming out in that spatial sense. The final component which I'll show you is the grade tonnage curve component. So in this case we are determining a primary attribute. So it varies a little bit from the old or the existing grade tonnage curves in that rather than having each of the variables defined by their own cutoffs, we define a primary attribute and the cutoffs for that primary attribute, and I'll just leave them as the defaults. And from that attribute we can then determine the various grade tonnage curves for tonnage, iron itself, alumina, silica and manganese. And in addition we've also added some percentile lines so that you can see the spread of the simulations across the different percentiles and across the mean of that attribute, and get an idea of how variable each of your simulations are at each of those cutoffs. So that concludes the demonstration today. If you have any other questions or queries, please feel free to contact us through our support desk or refer to their help documentation and other videos for more information.